So as mentioned, I'm going to be presenting a talk on occupant-centric light exposure in buildings. A little bit about my background before I launch in. So I am an assistant professor of architecture at the University of Oregon, and I also co-direct an institute called the Institute for Health in the Built Environment, which is a multi-lab interdisciplinary endeavor centered in the College of Design with a focus on applied information in the built environment. My background is I'm trained as an architectural designer, and in my research, focus on applications of building science. And so my main focus is on daylighting research, but also applications of electric light to supplement daylight in the built environment. Okay, so I always need to start with a conflict of interest disclaimer. I'm also a director of design at Oculite Dynamics, which is a company that provides consulting work for human-centric daylight design. And so some of the work that I will be showing is also covering content from that consulting work in addition to my role at the University of Oregon. So it's often easy to identify when there is too little daylight. And I realize I'm speaking to an audience that covers different geographical centers here. But this is a landscape that is still, in some cases, you can find this in the United States in office buildings. We went through a period of time where we designed very deep floor plates with very little access to natural light. And these became quite ubiquitous work environments for a lot of people. So almost no daylight present, probably very little access to view anywhere on this floor plate, and a huge sort of reliance on artificial or electric lighting sources. I would say it's also somewhat easy, I would say somewhat, to identify when there is too much light. So if we are looking at, daylight exposure as a spectrum from needing just a minimum amount of light to see and execute a task to avoiding so much daylight that we are at risk for disability from glare. This is quite a broad spectrum in terms of light level. And so obviously sitting on a perimeter, facing outside, staring directly at the sun is going to be uncomfortable for a vast majority of people. And so when we're talking about light exposure from the perspective of biological needs and circadian entrainment, and this is a webinar when a lot of people on this call are familiar with this topic already, but we have these non-visual responses, which are both circadian in nature and direct. And so the signals that the eye is taking into the brain, including sort of the intensity of a light source, its wavelength or color, the duration of that exposure, the timing of that exposure, and the history. And this is quite a complex signal in terms of components that make up that sort of light dose at the eye. And so it's been a difficult thing, I think, for us to bring into the built environment in terms of lighting recommendations, because it's not just as simple as some quantity at the eye as an average, across the day, or, as it happens at the eye level, we have to take into account the fact that the eye is moving and people are actually moving through a space as well. So it's not a static single signal or a quantity. And in terms of that light source that is coming into the eye, and we have recommendations for what that should be sort of at eye level and over time. But all these different components of the built environment are impacting that. So we have the light source itself, whether it's the sun or it's being impacted by weather, such as cloud condition, atmospheric effects, the lamp source technology that's been selected, and what the spectral component or distribution of light energy in that source is, as well as building materials themselves are creating sort of a light fixture for the eye, if you want to think about it that way. So all of the light coming into a space is interacting with surfaces that have the potential to absorb, reflect, shift sort of that color and intensity. And so we have several different metrics for the built environment, more specifically. And so if we're talking about how to evaluate this, we have circadian stimulus, which is the effectiveness of spectrally weighted irradiance of the cornea. We have equivalent melanopic lux, which is still used more in the United States. That was the first metric to be integrated into the WELL standard. And that would be lux weighted to the melanopic rather than the photopic sensitivity curve. We have melanopic equivalent daylight illuminance, MEDI, which has also more recently been added to the WELL standards, also the CIE standards. And then a metric called non-visual direct response. You'll see some of this integrated in some of the work I do as well, which came out of the EPFL with a colleague of mine that has been working on this. And that's a metric that kind of integrates information over time. So it's not a static number so much as something that integrates exposure and timing. So there are some commercially available tools that I'm sure a lot of folks on this call are familiar with. So Lemma developed a tool called Alpha, which allows you to understand the kind of melanopic versus photopic impact of a light exposure in any direction. So at this point in time, it is still sort of a static number, or static in the sense of temporal effects. It's a single sort of moment of time, and you can kind of hover over different view directions and then understand what that sort of quantity of light is, integrating the color aspect of different light sources and materials in the field of view. The company that I mentioned previously, Oculate, also has developed this kind of front-end interface for visualizing more kind of holistic lighting metrics, including this health-based metric, which we called vitality. That's that non-visual direct response metric. And so in this case, you're just seeing, again, singular view directions that are color-coded based off of a light dose exposure. So the darker green would be our sort of recommended dose, and that's meaning that you could meet your circadian exposure needs in either 4 hours of morning or afternoon light. And then that light green would be that you'd really need that whole sort of 8-hour window to meet that exposure target. So it's a kind of intermediate dose. And we've been using these to evaluate projects in the United States and Europe to give people sort of an overview of understanding of this biological need from a light source perspective, and integrating other metrics like glare and visual interest as well. And so where I became really interested in human behavior was working in this space where I like to tell people that this horizontal grid of points we simulate light in, that's really the problem, because we're not understanding light from a human perspective. And what I realize we've kind of continued to create in the field is essentially a horizontal plane of points, albeit they're at eye level and they represent different view directions, but they're still considering space as this kind of container that light is existing in, and not so much what we're actually being exposed to. So we wanted to start playing around with the idea that different people are actually exposed to very different light quantities in a space over time, and that the architecture is influencing that. The interior design in terms of seating, view direction, surface finishes is impacting that, but the actual populations could be very different based off of where they're using space and how they're using space over time. And so these are just some graphics that we developed for a prize entry for the La Trobe in 2019. But we became really interested in this idea that some spaces are designed to be more connected between individuals or subpopulations of individuals, so they're free to move within a space. And that also means that they have access potentially to multiple different facade directions in terms of daylight exposure. And some spaces are much more insular. So you might have a population that only occupies the east side of the building or only occupies the west or the south sides. And that these actually are going to, over time, create very distinct kind of populations of users. And there's a lot of different factors that can impact light exposure within that. So you have architectural factors like walls, transitions like doors, hallways, and then windows. And you also have programmatic factors, so how far a desk is located from the window, the density of seating, the view direction and proximity of occupants to one another, as well as different adjacencies, which might impact, spaces that people are more likely to use over the course of the day. There are social factors as well, which my team has not gotten into researching very much. I always like to mention them because I think these are really interesting. Is that I think there are potentially personality types like socializers or avoiders that might impact this light exposure information as well. So people that are more drawn to communal lunches that might be in a space that's better lit, whereas those that like to eat lunch by their desk, for example. And so we started this work a couple years ago with a study that we did with SRG Architects with their Portland office space. And so this is a 2-story office space with a southeast facing bank of windows along one side, and you can see it's double height, through the rest with this sort of mezzanine level on the second floor. And we were really interested in trying to evaluate what typical employees might be exposed to in this space. And so we established a simulation position at every seated view position. So these were both the workstations as well as spaces like the conference rooms or the lunch spaces. And we simulated clear and overcast sky conditions in 15-minute time intervals between 6 a.m. and 6 p.m. on key dates, June 21st, December 21st, and March 20th. And in this case, we were focused on, we simulated all the view directions, but we use this as a database to then pull individual profiles out of. So in this kind of first scope of work, we established these four, what I'll call like hypothetical or typical profiles. So we have a senior manager, which is in the red, and that individual would be sitting closest to the window wall in maybe more of a preferred or desirable view spot. They would take meetings kind of in and out of this kind of pinup space under the mezzanine level, taking lunch breaks, but again, in meetings where they might have their pick of the seating. And then a junior manager who is still located in that double height space, but perhaps sitting a little bit farther from the window wall, closer to the kind of bullpen of pinup space. We had an IT manager, which is our sort of cave dweller who would sit in the kind of IT server space and would kind of be coming in and out to address IT issues throughout the day, as well as an intern profile who sits up in the kind of nosebleed section of the mezzanine and is spending a lot of time in the laser cutting room and model building space. And I would like to add that these are intentionally sort of a little bit tongue in cheek, in that I know that there's quite a bit of diversity of how people are going to be seated in space, and this could be project-based, for example, and not so hierarchical, but we were sort of creating these as a first look to just see difference between types of profiles. So this is the senior manager. And in this case, we were evaluating equivalent melanopic lux and using a 200 EML threshold, which was the well recommendation at the time. And when it's yellow, you can see they cross that threshold, and when it's gray, they don't. So that senior manager is crossing that threshold from daylight only quite most of the time. And then the IT manager has these kind of pulses of darkness and light where they come in and out of that sort of server space. The intern is sort of gray all the time, except for that one little moment where they come out for lunch and they get sort of a hit of light, and then they go back into the kind of darker spaces. And so if we look at these, kind of, this is the senior manager where, according to the well standard at the time, they need a continuous light exposure over 200 EML between 9 a.m. and 1 p.m., which they do achieve. And then we're also showing that metric below this, that non-visual direct response, which is cumulative. So at the point in time when it turns green, it means that the daily dose has been met, which it does kind of around 130, 145 in this case. This, of course, is the less privileged intern profile. So they are getting that 200 threshold met almost never in the morning, except for that kind of lunch period where they come into the brighter space. And they are not getting that cumulative dose met at any point in time during those office hours. This is the IT manager, which is, again, that cave dweller, which is going in and out of those dark and brighter spaces. And so they are not achieving well based on continuous exposure. But you can also see that that line is not very far below that threshold. And so they are still, if you add up the kind of cumulative dose of those pulses over time, which can be, as we know, effective. It doesn't need to be continuous. They're still achieving that sort of daily dose. And so we published this as a paper in a simulation-based conference, and kind of did so as a way of just cracking open into this conversation with designers about the importance of understanding lighting performance at the population level. So it's not enough to just say some percentage of the floor plate gets light, but we really need to understand what percentage of occupants in that building are actually being exposed to high quality light at the eye. And so we got a lot of questions in that about, well, what about electric lights? I'm sure electric lights are providing the sample event that's needed. And so we were really curious on extending this research, which we did so in a follow-up study. We worked with a lighting designer in this space, Lisa Pedersen, who provided us with all of the information for the different lamp sources and fixtures. And we integrated those files into the simulation. And so it's a lot of direct, indirect lighting along the ceiling, as well as some wall washing, indirect lighting in the meeting spaces, and in some of the private office spaces. as well as the conference room. We developed a short survey, which we sent out to employees. We got about 38 responses from those employees. And they gave us information like what time they arrive at work. They indicated their seating position on a map, which we could then categorize them as more perimeter dwellers or more core dwellers. We asked them questions about like how many meetings they would take in a day, and if those would be more design-based active meetings, kind of conference-style meetings, meetings at their desk, and then we generated these profiles for each individual. Acknowledging, of course, that these would be quite dynamic in a real world setting, and so these just represent kind of a snapshot from what the survey could tell us. But you already see quite a bit of range and granularity now, even in terms of what time people arrive in the office. So that morning light exposure might matter more for some than it does for others. And then we created these individual profiles for each one. So you can see that there's some folks that arrive at 7 a.m. And are spending a lot of their time kind of working on the core, but perhaps meeting more in the perimeter, and other folks that are spending more time sort of meeting in the core as well, and for longer periods of time, right? And so quite a bit of difference in whether or not these people are exposed to sort of daylight and electric light, or they're relying more on electric light exposure. And so this is looking at sort of a map of all 38 occupants, the well credit, and I keep indicating this because this is sort of where we're at in the United States, at least in terms of being able to apply this in the building industry and get some kind of monetary or value-based credit out of it for designers. But this is looking at that period of time from 9 a.m. to 1 p.m. On March 21st under overcast skies. And if anybody's familiar with the Pacific Northwest, you'll know that overcast skies are pretty much our only sky condition, from November really through March. So we have a very, very cloudy winter and a very, very sunny summer. And in this case, very few people are achieving that recommended light exposure level at EML 200. We'll talk a little bit later about that value is actually higher now. And when we turn on the electric lighting, so to speak, so we add in that supplemental dose and compare those, we can see that it really tops out a lot of those profiles, but we still have some that are deficient. And they might only be deficient for a couple of 15-minute sections during the day, but that could add up to an hour, or in some cases even 3 or 4 hours of insufficient light exposure, even with that high, that LED lighting turned on. And so as a kind of proximity of, or as a sort of overview of this to look at the population, if we take a step back, overcast skies are going to perform a lot worse than clear. And of course, we have more overcast skies in the winter and fall and spring months in the Pacific Northwest. So in that case, even with electric lighting, we're getting sort of less than 25% of people that are meeting that recommended kind of exposure level as per WELS guidelines. And even under clear skies with electric lighting, it's around 50%. So very few people are achieving that 200 EML threshold throughout the day. And so I'm going to shift a little bit to some work now that we have done. We've sort of been tied. Whenever I present this work, I think about, well, like what should that threshold be, right? If we have some wiggle room to what the actual exposure number is, right? And I think that there's more and more consensus around sort of 250 lux at the eye level, but also some flexibility in terms of actual timing and exposure. So that doesn't have to happen between 9 and 1. It could be 4 hours, of relative morning, or sort of a longer exposure period of time, right? So I'd be curious to hear questions about this. But we've been really struggling with how to communicate this and how to take these metrics that are a bit complex for a designer to understand and be able to visualize it in terms that they can sort of understand, oh, this is something that is dynamic and we need to understand at the occupant level as well as this kind of temporal level. And so we had the opportunity, Oculite Dynamics did, to do this project with Meyer Partners a couple of years ago, where they were really interested in taking a look at some of their projects, which have been very much designed around daylight as a primary design feature. And we were looking at this project they had in Miami, Florida, which is luxury residential. So by all means, like very good light exposure compared to many residential projects. And we compared these two very different kinds of penthouse spaces. So one that's a 2-floor kind of south-facing space versus a more matte kind of deeper floor plate that has light exposure on 3 sides. And so this is a sort of look at the sort of NVRD. So this is that cumulative response metric that I mentioned previously. And so the dark green would be those kind of recommended dose, whereas the light green is that intermediate, and gray would be insufficient. So the perimeter is getting lit up with a lot of those view directions where we have access to the facade. And then you can see on the double height space, we have green pretty much throughout everywhere except for like the bathroom, which is tucked away from the window. So this one is just overpowered with a lot of natural light. And this was a project where we were really focused on the visual communication of this. So we created these little animations of an occupant, a typical occupant, as they would sort of wander around this space. So this is somebody who would wake up on the east. They had that little moment of darkness as they went into the bathroom. And then they're spending time moving around this penthouse, maybe working from home in different locations. But you can really see that the light exposure level is very, very high throughout the space, pretty much regardless of where they go after a certain point in time, especially obviously in this penthouse balcony facing the ocean, and even on the mezzanine level up here. So very high levels of light exposure throughout the day. And if you look at it kind of as this little thumbnail series, you can see that there's really only that one dip in the morning, and assuming that this is looking at daylight only, you would obviously have some electric light on in that space, but very, very high levels of light available at eye level throughout the entire residence. And then this is us looking at sort of 2 different profiles in more of that matte space. So we're going to call the perimeter dweller. So this is somebody who, again, woke up on the east, is going in and out of their kitchen and then working from home in this office that has a lot of light exposure to the perimeter. And it has lower light exposure than the other apartment that I showed you, but also very high light exposure throughout. So very much crossing that threshold of recommended exposure level and staying pretty much above that throughout that exposure window. And so again, this is showing a space with a lot of perimeter lighting available from a daylight perspective, and we're crossing that recommended threshold. Now we decided to compare this to a core dweller, and we kind of refer to this as the pandemic teenager. We did this work kind of during COVID, and so this sort of work from home mentality was very much present throughout this. And this was looking at the kind of teenager who might emerge in and out of the darkness to snack in the kitchen and have their food and caffeine needs met. But they're going to return back to this kind of entertainment media zone in the center, where maybe they are doing online school or they are watching TV or doing some kind of entertainment, but are otherwise not exposed to that kind of high quality perimeter lighting. And so this was really just to illustrate that 2 individuals living in a very well lit residential space could have 2 vastly different light exposure realities. And so behavior is really important to understand. And so side by side, we can see that perimeter dweller versus the core dweller. And I think, I don't know that a lot of people feel large amounts of empathy for these individuals as 2 different people that are experiencing this because they have the freedom to move to other spaces in this residential environment and receive higher level light exposure. But if we think about this as a school or a prison or a space, a healthcare space where you do not have the ability perhaps to move out of a space that you've been assigned, this is when the population dynamics of these users might become really valuable and important to understand. And so I'm gonna kind of present 2 more projects here briefly, just for the sake of discussion. And all of these are kind of taking a slightly different angle around this idea of behavior. So this is a paper that we presented in Shanghai at Building Sim in 2023. And this was kind of more of like could we come up with a really simple sort of weighted approach to this behavioral idea that would be easier for people to implement, as opposed to having to understand the granularity of where people go all the time. So we created these 2 different building typologies, a courtyard space and a box space. So we're calling with no core penetrations. For the sake of simplicity, we assume this is a 1-story office structure. And we also compared this kind of opaque interior partitions versus glass partitions. So the opaque would not let light from the perimeter into the rest of the space, whereas the glass would. And then we had folks that would be sitting at open office workstations as well as more private offices on the perimeter. We developed these kind of profiles and then created a kind of weighting mechanism for the class of each profile. So we started with a manager level profile, which would be sitting on an exterior private office and would be taking meetings throughout the day in these different meeting rooms and then taking a lunch break in this sort of lounge space. And we created profiles that would cover each kind of seating class or occupant class in the space, and then assigned a number of occupants based off of the furniture layout. So what you would need to do in order to implement this is sort of determine the sort of different types of profiles in terms of space use. And then you could say that this profile applied to 8 occupants in this space based off of the orientation of where they're sitting and how many offices are located in that same orientation. And then what we did is we simulated equivalent melanopic lux, and in this case, we were looking at a couple of different thresholds. This image is just showing the 150 EML threshold, which is quite low, I think, relatively speaking. But from well would get you sort of that first single credit, not the 3 credits. And if you look at this, we're looking at clear skies is blue and cloudy skies is gray. June 21st, September 21st, and December 21st for each of these scenarios. And so what this is essentially is the percentage of occupants that are achieving that exposure for 4 hours. We did do this one. This is a bit more complicated the way we simulated this. We did a sliding window, so it doesn't have to be 9 a.m. to 1. It could be any 4 hours of continuous light starting by noon at the latest. And so you can see in June and September, the courtyard building with all of the kind of glass intermediate walls achieved that dose for 100% of the occupants. We started to see some drop off in the winter under the cloudy sky conditions. And then as we move to the right down this graphic, we can see that as you implement solid walls, we're starting to see a percentage of that occupant performance drop, as well as the box where it has the kind of no core penetration. With the glass walls, it's dropping quite a bit, especially under the overcast sky conditions. And then when it's a box of solid walls, it's dropping pretty much all the way. So less than 50% of occupants in the best case scenario are achieving that recommended light dose. We tried to break this down in a couple different ways in this paper. And I would say a lot of the work that I'm doing right now is just exploring ways of trying to quantify or synthesize this information. So these green bars are showing the potential of achieving that dose from daylight versus the gray bar is going to be the percent that would require some form of electric lighting as a supplement. And so the green, right, if it's fully charged, it means that dose is being achieved from daylight only, and that's what we'd like to see. And then as we get more and more levels of gray as we go into the winter, as well as we go between different sort of sky conditions, you can see that electric light would be relied upon for almost everybody in that case. And then this is the last project that I'll show. This is the one that focuses really more on electric lighting as a source. So this is a project that we did, my lab at Oregon did with NIA on an luminaire level lighting control system, an LLLC, as I might call it. And so this is a LLC lighting design that was implemented in their office workspaces in Portland. And so they do have this kind of perimeter band of daylight that is available around the entire floor plan of this building. And then this LLLC lighting system that's installed at the ceiling, which is a direct system. And it means that there are sensors available sort of at every light fixture that allow them to really control the light dimming on and off at quite a granular level. We developed a simulation workflow for this project, which used components of LARC and Radiance. And we integrated this into a single sort of simulation protocol for both daylight and electric lighting sources. And it allowed us to output a number of different metrics like daylight availability and excessiveness. But we also implemented this equivalent melanopic lux level into the system. And it allows us to calculate the contributions of both daylight and electric light on the circadian potential for a series of different workstations, as well as the energy required to meet those thresholds. So every time we turned on a light, we would essentially add up that wattage, and we could compare the energy intensity of sort of supplementing the light level, the exposure level at eye level, using these electric lighting sources. And we also compared different control and shading scenarios throughout the year. So for those that are not familiar with the simulation side of this, Radiance typically produces 3 channels of spectrum, this kind of really crude RGB. And LARC allows us to break each of those channels down into these triplicates. So we essentially have a 9-channel accuracy, which is much preferred as kind of a minimum when we're doing circadian simulations with electric light, because it's going to allow us to capture the sort of granularity of the spectrum of those different lamp sources more accurately. So as I mentioned, we did it for this office space that had 88 workstations. The seating orientations were primarily east-west with some north-south. They had 8 different zones of this LLC lighting and manual shading systems on the perimeter. And so we simulated the eye level EML for all workstations for all hours of the year. And we also initiated an automatic blind schedule that would go up and down based on its design, and 10 steps of dimming for each zone, right? So we produced a lot of data in this project. This is just an overview of these seated positions throughout the floor plan. So none of them are really that far from the perimeter. They all have some access to daylight on the east, kind of south and west facades. And I'm going to start with just a quick overview of the kind of percentage of the time of year between 9 a.m. and 1 that this EML 275 lux, right? You'll see these thresholds shifting throughout this research as recommendations change. But this is this kind of higher level sort of threshold, which is more equivalent to this 250 MEDI. And so you can see a lot of these positions at the core are achieving near 100% of the time where they're getting that sort of met from daylight. And then that's dropping as those view positions get farther from the window. And when we operate blinds, it drops even further. So that blind control is taking away some of that daylight access at the eye. These are the different lighting control groups that existed. So they're kind of banked based off of orientation throughout the space and seating cluster. And so what we did is in our simulation, if we had any of the desks that dropped below the recommended light dose, which was 275 and sometimes 150, we were able to turn on that light source and then kind of top up the dose and then add up all the energy that would take. So this is just kind of looking at, this is that first 150 EML threshold, so the lower of the two. And this is no shading, no task lighting. And basically the percentage of electric lights that would need to be dimmed all the way up, right? So red would be 100% of the lights are on in order to try to top up the dose. So morning in the winter, not surprisingly, that electric light is almost always on to be able to top up the dose. When we go to shading, right, we've added shading into the window. We now have much higher percentage of the time in those sort of shoulder season in the winter that we need the lighting on more frequently to top up that dose. This is that 275 EML, so this is more of the recommended level. And you can see now that we need electric lighting on all the time. So it's pretty much burning out between 9 and 11 through the winter months. 100% of the lights are going to be on to top up that dose, with very few instances where those lights can go fully off. And then when we add in shading, again, it's almost the entire year. So some periods of time where maybe we've got 75% dimming, but for the most part, it's up all the way. And when we just compare the monthly energy use total between those morning hours in particular, we can see that based off which threshold we're trying to meet, right? If we're only going for an 150 EML at eye level, which is the lower of those two thresholds, then we can save energy in the summer, right? We can really use that daylight harvesting to enable the light system to dim down. If we're going for the higher threshold, kind of regardless of shading or task lighting scenario, it's on most of the time. And there's a number of reasons for that. It has to do with the fact that our overhead lighting systems are not designed to be providing 250 or 275 lux in the field of view. It's much higher than the lighting recommendations that the systems were designed for. And so they're maxing out essentially and taking very little advantage of that dimming control. And I just got a couple of slides left here, but this is just a comparison between the 150 and the 275 target. So as a percentage of annual energy, you can see that if we have no shading systems deployed, we can essentially save quite a bit of energy from a circadian perspective because we're not kind of removing that vertical light source out of the field of view. And when we jump up to that 275, there's very little difference kind of between those lighting scenarios because, as I mentioned, we need to supplement quite a lot of electric light to get over that recommended threshold. And then all the way to the right, we did just a kind of a comparison between an LLC and an on-off switch lighting to meet this kind of horizontal work plane target. So this would be what a designer would be looking at just to meet workplace requirements at the desk level. And you can also see that that's going to be quite a bit lower than that 275 operation. So if you're designing electric lighting for general office requirements, that's going to be less energy intensive than if you're designing it to meet these kind of eye-level circadian targets. And then just, did we meet the target is a question at the end. So if we're only targeting 150 EML at the eye, we can see there's throughout the summer quite a bit of times that are at that 100% and a lot that are kind of in the high 90s as a percentage of the workstations that met the target. When we add in shading, it drops a bit. When we look at the 275 target, we see it dropped substantially. So very few times where 100% of the workstations are achieving the target. They're more sort of in the sort of 80s to 90s or down below 50% in the winter. When we add in shading, again, it drops even more. And then if we compare it just to horizontal lux, so the graphic on the left here is that assuming we would be operating a lighting system to meet 300 lux, right, which is a sort of typical office design target in the United States. And looking at it kind of a percentage of workstations that meet the threshold is that orange line. So if we're operating it to meet 300 lux, then, often 50% or less of those workstations are actually meeting that eye level target. If we're to operate it to meet at 275 lux, right, so we're maxing out the lighting system as much as we can, we still have quite a few times where that threshold is not met. So it's often met in the summer for a large percentage of the workstations, but we can see that drop off in the winter. So this is really just to say that even in a modern application of high output LED lighting with smart controls, a large percentage of the workstations are still not meeting that recommended target or expending lots of energy in order to try to do so. So that kind of has brought me, and this is the kind of closing research slide I'll show, is like, what should those targets be, right? If we're going for 275 EML or 250 lux, more simply at eye level, are we trying to achieve that for 100% of the workstations at 100% of the time, or is there some flexibility to that? Because if we're only trying to achieve 75% of the workstations, that becomes much more achievable when we combine, smart lighting controls and daylight. But if we try to achieve 90, 100%, it's really impossible to do. And it might encourage people to be implementing very energy intensive lighting systems in order to try to achieve that. And so that's just kind of a question that my lab has been struggling with quite a bit. So some of the next steps for us are to integrate more robust occupancy modeling techniques to create more granular predictions of eye-level light exposure across a population of indoor occupants. We want to explore the impact of common design parameters on eye-level light exposure to establish more simplified rules of thumb. I think you've seen a kind of a range of modeling techniques that we've used, and I think most all of them are really impractical from a typical design professional's perspective. We want to expand these methods to real-world scenarios to validate occupancy models and eye-level exposure predictions in physical environments. And I think there's probably some folks on the call that could help us with this. And then develop annual metrics that capture eye-level light exposure across a dynamic population, either for some percentage of users, some percentage of time, and what exactly is that threshold level? Is there any flexibility to it? And finally, I want to challenge some of these implementation recommendations for organizations like WELL to be able to balance the health and the energy savings from electric lighting more holistically. So it might be about promoting daylight more, looking at where we can maximize daylight as a source, but I'm concerned a bit about how the electric lighting industry is kind of taking these recommendations and using it as an excuse to recommend very high levels of electric lighting use. So that is where I will wrap it up, and I'm happy to take any questions at this time.
Wonderful. Thank you so much, Chevy. Great talk. I think really, really important, and also, timely, because I think the research has moved to a direction where we really need to apply the knowledge. And I think this is exactly what you're doing here, in a way that still doesn't make it, trivial, and sort of, dumbs it down to the extent that actually the human component is taken out. So we got two questions, one from Sue Cross. Sue wants to know, what is the LARC circadian dosing calculation?
Yeah. So LARC is a software that was developed by Malika Inanici's team at University of Washington. And it's kind of an open source sort of grasshopper plugin for Rhino. So it allows you to bring radiance as well as this kind of the 9-channel spectral component technology to that. And so it actually is quite flexible. It produces a number of different metrics in that engine. And so we were pulling the sort of Lucas application of that equivalent melanopic lux. There's also Rhea's work integrated in there. And so it outputs a number of different metrics that you can use, as well as more traditional metrics like horizontal luminance, and we also added in glare into ours. So what number you pull from it is kind of up to you, but it allows some flexibility in that.
Great, thank you. We got a question from Jamie Zeitzer. Jamie wants to know, do you have any functional outcomes to indicate which thresholds in a functional setting are actually accurate?
No, I do not. And I'm really interested in what those might be. I think that there's a lot of folks working on that at different levels, coming from different fields. My sort of suspicion, from what I understand about the more complex models that integrate exposure over time, is that we don't need to be achieving the recommended threshold continuously, is that we could probably get away with some levels that dip at certain parts of time and other light exposure levels that are higher. And functionally, we don't have a lot of field information about what that actually needs to be. There's also probably interpersonal differences, right? So what it might be for one population might vary quite a bit by age or even exposure history, right? So I think this is a very good question, and I don't have a great answer for it.
Great. Got one question from Tony Esposito from the chat. He is the light concept lead as IWBI, the providers of the well building standard. He asks, what recommendations do you have, if any, for changes to the well building standard? And he's currently wrestling with a similar question about what percentage of workstations should be required to comply with stated thresholds. He's put his email address in the chat. So
okay, great.
But yeah, go ahead.
So I love this question, and I think a lot about. I don't have the answer for it currently, but I have a lot of ideas for what one could look at. So I think that the continuous light exposure requirement, like needing to meet that for 4 hours, sort of every day of the year, is really difficult to achieve in practice. And so I think there needs to be some flexibility built into that. And I'm not exactly sure what the threshold should be. I think we need some field verification to understand that and inform that. But I would say that being able to achieve that recommended threshold for a percentage of time, let's say it's 90% of the time for 75% of people, that might actually be an achievable target. And so it's something that designers are going to want to take on. Currently, even you could see when we turn that electric lighting system on at full output, in that last study that I showed, we're still not achieving that for 100% of folks. So I think if a designer sees that the recommended implementation is impossible to fully achieve, they're not going to try at all, right? And I think that's worse, is we need to create targets that are achievable, that still kind of balance that energy savings side of the equation to make that target something that people are willing to sort of prioritize. And I'd be happy to reach out more about that, because I think in our studies, when we look at even a metric like spatial daylight autonomy, or SDA, it's looking at percentage of the time for a percentage of the space. And I think that the circadian metrics need to kind of move in that direction, although I'm TBD on what the percentage of time is and what the percentage of occupants is. To make sure I capture. If I don't, I can't see the chat right now, I guess, when I'm sharing, or just because I'm. Oh no, I can see
Tony
it.
just put a thumbs up, so I think the answer was what was good. So, but I think he'll, if you want to reach out to him, I think his email is also in the chat.
Sounds great. Yep.
Are there any other questions for Chevy?
I'm also happy to just chat about this a little bit longer. I mean, I think my lab has really struggled with balancing the sort of accuracy and, do we lean more in the side of like having a very robust behavioral data set with high levels of accuracy on light exposure versus a sort of more rules of thumb, rougher overview of performance in a way that we can simplify that output in a way that's easier for people to replicate and to understand. And I think I used to think I had to choose between them, and now I think it's a both and scenario where I think we need both of those. I think we need more accuracy to really understand what people are being exposed to and how different those scenarios are across the population. And we also need rougher, sort of more synthetic methods that just allow us to understand this in simpler terms. Because I think from my experience, we overwhelm people with the amount of data and the number of scenarios. It just makes them kind of think, wow, this is a really challenging thing to absorb and understand. And I think we need folks to understand that it's complex, but also see that there are real scenarios that they could implement to improve this in a practical sense in buildings. So
yeah, I mean, I think it's a very nice point. I mean, I think there's this question of like, how do you make this accessible and actionable without losing the complexity, right? And I think like on the spectrum, you can you can find yourself either saying, oh, it's too complex, and then you never will get anything done, right? Because it's always going to be like, well, you don't know where your faces look or where your head is moving to and your eyes are moving and whatever, right? Or, you of course, and I think most people working in this field will acknowledge that a spatially integrated irradiance measure is not sufficient either, right? And so like somewhere in the middle is probably where we want to be technically and also scientifically.
Right. Well, no, there's also an aspect of this that we don't need, high levels of light exposure in every view direction and every seated position in a space. We can also encourage folks to use the space in a way that's more effective for their daylight dosing. And so that might also be understanding what spaces are going to attract people so they could kind of top up a light dose. And so I keep talking about like the watering hole or the coffee station. If we had a lot of high level daylight at a place that was attracting people habitually over the day, that might have a bigger impact than trying to achieve high level light exposure at 100% of the workstations. So it's just, there's a lot of components about this that are actually really important for the design community to understand. And I can see a follow-up question from Tony. How accurate is the modeling of EML and MEDI? Yeah, that's a great question. I also think there's this aspect of accuracy that's simulation based. So if we're talking about the spectral accuracy, what I showed was a 9-channel spectral accuracy, and that's going to be more accurate than 3-channel, but there's also alpha uses 81 channels, so that's even more accuracy spectrally. And that matters more for dimmer light sources than it does for daylight, because daylight, the intensity is so much higher that's generally driving the dose more than the kind of spectral component. But when we're talking about electric lighting and dimmable systems, then the spectrum starts to really matter. We have done a little bit of comparison between image-based versus sort of sensor-based calculations, and we see quite a big range actually of sort of difference. I don't know which one's more accurate, to be honest, but we see quite a bit of difference between those strategies. So I think that's a good follow-up question, and maybe something we need to try to publish that. Yeah, so I see also from Sue. Is it okay if I just read these, Manuel? Is that
Yeah, I think
okay?
you've already answered the two ones that are in the Q&A. I just didn't make them inactive.
Okay, yeah.
But I mean, if there's any other, there's one question from Carolina just in the chat.
Mm-hmm.
I don't know if you can see the chat. So she's asking what can be done for promoting more spaces where people can move from their designated space into other spaces for eating, drinking, or just taking a break.
Yeah. I think that's a great question. And I think, where this work gets a lot of interesting discussion is in communities of interior architecture, interior designers, because they're very focused on the human aspects of space use in general. And I think they've been really interested in talking about, well, is it just about bringing people out of more darker environments into light environments, using things like eating or drinking as a sort of attractor? And I think that's a really interesting thing that needs to be explored further. So I would say if we look at spaces that habitually draw folks throughout the day, and that might be like the coffee station, bathrooms even, and those are typically actually located in the like darker portions of the building, are not necessarily given that sort of real estate of that high level daylight. But maybe if we flip that a little bit, we could actually get more light to people more consistently throughout the day. So I think it's about making really beautiful spaces that attract people. I think that's the answer, is make them want to go there. And they shouldn't have to go there. It shouldn't be something where like, well, I need a circadian top up. I better go stand by that window. It has to be that it's a beautiful space and it encourages me to want to go there anyway. And then at the same time, it has the co-benefit of providing light exposure that I need.
Great.
Mm-hmm.
I think we're probably at the end of questions. So thank you again for giving a great talk. I think really nice to see this work. Looking forward to also welcoming you in Munich. I think this will be fun. And then, yeah, so thanks again. And everyone else you can now disconnect. And
Thanks, everyone.
quickly stay on the call. We'll have a quick meet and greet with the
Sure.
team. Thank you.